Hi everybody. If you're watching this video, you are a student that's having a little issues with the periodic trends and getting a couple of things mixed up. So I wanted to make this video so that you could maybe understand it a little better. So I want you to put your earbuds in and pay attention as I go through here, and you can fill this out on your sheet of paper as I go through here. So firstly, you need to know that we have three periodic trends. There are three periodic trends. We're going to talk about electronegativity, ionization energy, and atomic radius. The first one is electronegativity. And electronegativity is simply how badly an element wants an electron. You can fill that in. How badly an element wants an electron. So the elements that are really, really close to the noble gases, those are going to have very high electronegativity. Similarly, ionization energy is how much energy is required to steal electrons. How much energy is required to steal electrons? So if an element really likes having the electrons that they do have, they are not going to want to give them away, and it's going to take a lot of energy to pull them out. In fact, the noble gases are going to have the highest ionization energy of any of them. So let me just show you what that is here. So this is my periodic table of elements. These right here are my noble gases. They really want to hold on to their electrons. So they have the highest ionization energy. However, the electronegativity is saying how badly does an element want an electron. These guys, the noble gases, they don't want any more electrons. They could care less if an electron came because they have all the ones that they need. So they have the highest ionization energy but the lowest electronegativity. Besides that, the noble gases follow the same trend as everybody else. So let's jump in here. Before we jump in too far, I just want to mention again that the third trend that we're going to talk about is the atomic radius, which is how big an element is. How big an element is. So, firstly, how badly an element wants an electron. This is going to be electronegativity. The trend of electronegativity is going to increase this direction. So you can, on your paper, you can draw an arrow going from the bottom left up to the top right, meaning that these elements up here are going to have the highest electronegativity of any of them. Let's do a couple. Which would be more electronegative? Remember, our electronegativity is increasing in this direction. So let's take chlorine versus sodium, okay? Chlorine versus sodium. Chlorine is here, and sodium is over here on the periodic chart. Therefore, chlorine is going to have the higher electronegativity. So we would say chlorine has more electronegativity. Let's look at strontium, okay? Strontium is here, and sodium is here. So our strontium is going to have lower electronegativity. So this would be the lowest, then sodium, then chlorine. And that's because strontium is here, sodium is here, and chlorine is here. So we're increasing in this direction. All right, let's move on to ionization energy. Ionization energy is, again, how much energy is required to pull away an electron. Now remember, I told you that these noble gases right here, they are going to have the highest ionization energy. Similarly to electronegativity, ionization energy is going to increase in the same direction. So this is the lowest, and this is going to be the highest. Let's look at this here. Same elements here. Electronegativity. Ionization energy. So we're not looking at electronegativity anymore. We are now looking at ionization energy. So let's jumble these up, throw a couple more in there. Which of these has the lowest ionization energy? So remember, our ionization energy increases in this direction. So chlorine is going to be up here, so that's not going to be the lowest. Fluorine is also in that up here. Strontium is pretty far down this way. Sulfur is up this way, and sodium. So we have the first two here. Let's move these out. Strontium and sodium. Strontium is here, and sodium is here. So strontium is going to have the lower ionization energy, then sodium. Now we need to decide between chlorine, sulfur, and fluorine. So chlorine, sulfur, and fluorine, these three. The next lowest is going to be sulfur, because we're moving up the arrow. Then we're going to have chlorine. Then we're going to have fluorine. So the question here is, why does ionization energy increase this direction? And the answer, if I can use this as an illustration, is because the energy required to steal an electron. Let's look at these two elements. So rubidium is down here, okay, right here, and lithium is here. Is it easier to steal an electron from this outer shell that's so far away from the protons, or is it easier to steal an electron right here that's so close to those protons? The answer is obviously it's easier to steal an electron when it's so far away from the thing that it's attracted to. I always use an analogy. If this is you and this is your purse, it's easier to steal money from your purse when it's far away than it is to steal money when your purse is super close to you. So maybe that helps you, maybe it doesn't. If it doesn't help you and it just confuses you, then just erase what I just said. And let's look at our last thing, which is atomic radius. Atomic radius is going to increase this direction. Okay, it's the only one that doesn't go in the way that we've been talking. So the smallest elements are up here, and the biggest elements are down here. I can use these same couple of elements here to illustrate why our fluorine atom, let me pull a couple things in here. The biggest question I have, and remember, we're increasing in this direction. So these are going to be the biggest elements. These are going to be the smallest elements. Elements are going to decrease in the left, they're going to increase this way. So as we go from left to right, they're going to decrease. The reason for that is because, if you look, lithium is here and fluorine is here. This is fluorine's Bohr diagram. This is lithium's Bohr diagram. The thing that you can tell that's different, so lithium is here and fluorine is here. They're on the same line. Let me use this as an analogy as to why fluorine is smaller. Fluorine is smaller because, if you notice, we still have, we have two rings of electrons. But the thing that's different is that this and these nuclei are vastly different in size. This nucleus is much, much bigger. We have a lot more protons in here. This nucleus is much, much smaller. Remember, these electrons that are circling, they're attracted to this. So the bigger the magnet, the closer those electrons are going to squeeze in towards the nucleus. Same thing here. This is the nucleus. These electrons are going to be a little bit further out because they're not quite as attracted to this smaller nucleus. All right, so that is my reasoning for telling you that we are going to increase our size of atom as we move from right to left, just on a period. We're going to increase as we move down a group. So this is lithium here, and rubidium is here. These are the Bohr diagrams. As you can see, rubidium has a lot more rings than lithium, and so rubidium is much, much bigger than lithium. So we're increasing this direction, and we're increasing in this direction. I hope that helps. If it doesn't, ask me questions. I'm always here. Obviously, go back and pause it if you have any, if you need to look at things again. And good luck on studying.